Hi, and welcome to this talk on polarization. If you get nothing else out of this talk, the statement at the top of this slide is the thing that you should get. The term polarization refers to the orientation of the electric field vector as a function of time. And since we're talking about waves, the change in the orientation of the electric field vector that we're talking about might equivalently be interpreted as a change over position along the path of propagation. I'm going to begin this talk with two common misunderstandings about the concept of wave polarization so that we can get them out of the way. The rest of the talk is about three broad classes of polarization, namely linear polarization, circular polarization, and elliptical polarization. Okay, first, the misunderstandings. The word polarization is sometimes applied to a particular property of materials. That is, many materials are comprised of molecules that have a net positive charge on one end of the molecule and a net negative charge on the other end of the molecule, and all the molecules tend to be aligned. In other words, we're talking about charge distributions, and the relevant concepts are described using terms like dielectric polarization, or dipolar polarization, or ionic polarization. These things are all properties of materials. They're not properties of waves. Another term that can cause some confusion is polarizability, and that refers to the ability of a material to become electrically or magnetically polarized. That also is not a property of waves. Furthermore, in quantum mechanics, we have the concept of spin polarization. Once again, not a property of electromagnetic waves. Now, a lot of folks understand that wave polarization is not the same as material polarization, but nevertheless have the conception that polarization refers to the orientation of the electric field vector. It does not. Polarization refers to the manner in which orientation changes over time, or changes over distance. In other words, there's no way that you can discern polarization unless you are able to observe the electric field at a point over some time span, or observe the electric field over a path at a fixed moment. You need to see how the orientation of the electric field changes. Okay, the simplest way that a wave can be polarized is called linear polarization. The idea is simple. The electric field remains in a plane. It might change sign, that is, point in the opposite direction for some part of a cycle and then return to the original orientation, but nevertheless, the vector always lies in a plane. In the picture shown in this slide, the wave is traveling to the right, that is the plus z direction. The electric field vector can exist in any direction perpendicular to the z-axis, and in this particular case, the electric field vector is x-directed. And if it's linearly polarized, it's always either plus x or minus x directed. That is, the electric field vector points in the plus x direction for some period of time, and the minus x direction for the remaining time. Since the plus x and minus x directions both lie in the y equals 0 plane, in other words, the electric field vector is always in the plane, it is linear polarization. Once this concept is described, most folks don't find linear polarization to be particularly surprising. And it isn't. For example, it seems logical that this is what you would get from something like a dipole antenna. Generally, linear polarization is what you expect to see any time that the current that gave rise to the field is accelerated along the line. For the astrophysicists, an example of a source that makes linear polarization is pulsars. Now, you should note that there are many possible planes in which the wave can be linearly polarized. In this figure, we show just one. I'll show you two others in a moment. In this figure, the electric field vector lies in the xz plane, or what you might call the y equals 0 plane. Since the vector points up or down, we might refer to this as vertical polarization. Why not? In fact, let's call it V polarization for short. To be clear, V polarization is linear polarization. Also to be clear, the orientation for V polarization is arbitrary. For example, for a radio wave traveling parallel to the Earth, you might say V polarization is when the electric field vector is perpendicular to the ground, and that would be typical and understandable. But don't be married to the idea that V always means vertical. This assignment is arbitrary and it depends on the application. Another way that a wave can be linearly polarized is shown here. In this case, the polarization is perpendicular to V polarization, so it makes sense to call this H, or horizontal polarization. But once again, V and H are just labels. It might not refer to any particular orientation with respect to ground or with respect to anything else. If we define V and then we define H to be perpendicular to V, then it turns out that all of the power in the wave will be a combination of V and H polarized power. This is because the electric field vector is always perpendicular to the direction of propagation. So all of the electric field is represented by some combination of V and H polarized components. Just to drive the point home, consider this odd-looking diagram. In this case, the electric field vector is in the pink-colored plane, which is tilted halfway between the x and y axes. Since the electric field vector lies in a plane, this is linear polarization. Now, is this V? Is it H? Or is it some combination of polarization components? The answer is, it depends. Before, V polarization was in the y equals 0 plane, that is, the electric field vector parallel to the x-axis. If we're sticking to that definition, then this wave contains V and H polarized components in equal amounts. On the other hand, we might define V to be in the plane of the electric field vector, in which case this wave is said to be fully V polarized with no H polarization. Or we could define H to be in the plane of the electric field vector, in which case this wave is said to be fully H polarized with no V polarization. Any of these definitions is fine, since the definitions of V and H are arbitrary. The only thing that is not up for debate, or for subsequent arbitrary assignment, is the fact that this wave is linearly polarized. Now, we move on to circular polarization. Here are two examples of circular polarization. In each case, the electric field vector does not remain in a plane, so this is clearly not linear polarization. Also, you see that the electric field vector magnitude remains constant. That's new. These are the two things that make this circular polarization, i.e., rotation of the electric field vector with time, or equivalently with distance, and 2, the magnitude of the electric field vector remains constant. The difference between these two images shown here is the direction of rotation. Here we're showing the two components of circular polarization. These two components are different in the direction of rotation. On the left, we have left circular polarization, which is abbreviated LCP. LCP is sometimes also referred to as left-handed circular polarization, abbreviated LHCP. This latter name gives you a clue as to why we refer to this as the left component of circular polarization. Try this. Extend your left hand with your thumb perpendicular to the fingers. Extend your thumb so that it points in the direction of propagation. Now your fingers point in the direction that the electric field vector rotates. That's it. That's why we call this LCP or LHCP. The figure on the right shows right circular polarization, abbreviated RCP or RHCP. Why do we call it that? Well, now extend your right hand with your thumb perpendicular to the fingers. Extend your thumb so that it points in the direction of propagation. Now your fingers point in the direction that the electric field vector rotates. That's why we call this RCP or RHCP. Recall that with linear polarization, we had V and H components. Now with circular polarization, we have LCP and RCP components. Furthermore, if the wave is circularly polarized, then it must be a sum of LCP and RCP components. Now, for linear polarization, V and H were arbitrary. We required only that they be in perpendicular planes. For circular, it appears that LCP and RCP are not arbitrary. After all, I just explained how to use your hands to define these components. There's something to be aware of, however. Every once in a while, you'll come across someone who defines LCP and RCP from the perspective of the receiver of the wave. That is, they will say LCP refers to the direction that the electric field vector rotates if you are located at the receiver and point your thumb in the direction of the approaching wave. This, of course, gives you exactly the opposite definition. Now, this isn't common in radio, but does show up in other wave bands and occasionally in radio. So be on the lookout for this. You might wonder what the heck it is that makes circularly polarized waves. This would seem to require currents that are moving in a circular fashion. And that certainly works. For example, that's essentially the definition of a helical antenna. So a helical antenna, or a helix, will give you LCP or RCP depending on the direction that the helix is wound. You might extend that thinking to loop antennas. However, this is incorrect. Loop antennas create linear polarization. An explanation for that will be deferred until we have a chance to explain how antennas work in a future lecture. Another antenna scheme that creates linear polarization is two dipoles arranged at right angles to each other and fed 90 degrees out of phase. You might be able to see why that generates circular polarization just based on that much information. However, again, I'll defer explanation of that to a future lecture. Certain astrophysical signals are circularly polarized. A well-known example is the decametric emission from Jupiter, which is intermittently observed in the HF band. Okay, now I'm getting ready to explain elliptical polarization. I'm going to start with this picture of a circularly polarized wave. The blue curve traces out the position of the tip of the electric field vector over time. The purple curve at the left is the projection of the blue curve onto the plane. Not surprisingly, the projection of the trajectory of the tip of the electric field vector is a circle. Here's that same process repeated for a wave which is elliptically polarized. Now we see that the projection of the trajectory of the tip of the electric field vector is an ellipse. In other words, if the magnitude of the electric field vector is constant as it rotates, we get circular polarization. If, on the other hand, the magnitude of the electric field vector varies as it rotates, then we get elliptical polarization. And that's really all there is to it. The thing that might stand out about elliptical polarization is that it would seem that there is a lot of ways that the magnitude of the electric field vector can change as it rotates. And that's absolutely true. In fact, circular polarization is merely a special case of elliptical polarization, namely the special case in which the magnitude of the electric field vector remains constant. Furthermore, note that linear polarization is also a special case of elliptical polarization, namely the special case in which the variation is so extreme that the magnitude of the vector is non-zero only in one plane. In other words, linear polarization is elliptical polarization in the special case that the purple projection curve has been compressed from an ellipse down to a line. Summing up, all polarization is actually elliptical. Linear and circular polarization are merely the extreme cases of elliptical polarization. And there are a continuum of possibilities in between linear and circular, corresponding to ellipses of various eccentricity. Okay, let's review. The term polarization, applied to a wave, refers to the change in the orientation of the electric field vector as a function of time, or equivalently as a function of distance along the direction of propagation. Polarization is not merely the orientation of the electric field vector. That's a common mistake. The three possibilities we considered were linear, circular, and elliptical polarization. We have linear polarization if the electric field vector is confined to a plane, and we explained how any linearly polarized wave can be viewed as the sum of arbitrarily defined v and h components. We have circular polarization if the electric field vector rotates while maintaining constant magnitude. And we explained how any circularly polarized wave can be viewed as the sum of LCP and RCP polarized components. Finally, we have elliptical polarization. The electric field vector rotates, but does not necessarily maintain constant magnitude. And we explained how this is actually the most general case, and how linear and circular polarization are merely extreme special cases of elliptical polarization. If you're interested in a deeper dive on the topic of wave polarization, which requires some more math, check out the reference at the bottom of this page, or any other decent textbook on electromagnetics. That concludes this talk on wave polarization. Thanks for listening.